Okay, we're going to look at reflections and rotations using matrices. And first thing we're going to do is come to the general reflection matrix, so rotating through theta degrees. So we're going to do this by the same principle we have looked at before, which was we want to see where the point 1, 0 goes to, and we also then want to see where the point 0, 1 goes to. And if we can find out where the images of 0, 1, 1, 0 and 0, 1 are, then we can push those together and that will form our matrix. Okay, so the first thing we're going to look at here is we're going to look at if we rotate the point 1, 0 by theta degrees anti-clockwise. So this wee length here is 1, so I'll just add a wee 1 in here to show you what that 1 really is from here to here. So if that's rotated, it goes around to here, so that diagonal is now 1, and this now is my point xy, and I want to find the coordinate of xy. So we're going to do this using a wee bit of trigonometry. So we'll get rid of this 1, this length is no longer 1. So we want to find what this x value is, and we want to find out what this y value is. If the angle is theta, then we can just say that cos theta is equal to adjacent over hypotenuse, so cos theta equals x over 1. That means we better rearranging, x is equal to cos theta, and likewise your sine theta is equal to y over 1, so y is equal to sine theta. So the x value is cos theta and the y value is sine theta. So basically we have found that 1, 0 goes to cos theta sine theta, and that's it. Okay, next of all we want to see where 0, 1 goes to. So it's a wee bit trickier, and this will be the same for the reflections. The 0, 1 is a trickier one to find out. So we'll just do our diagram here. We've got 0, 1, which is here, and if you rotate it by theta, remember this height here was 1, so when that rotates down, if that rotates down in this way, that means this length is going to be 1 here, and if it's rotated through theta, that's theta. By alternate angles, that will also be theta in here, and we want to find our x value, and we want to find our y value. So we can go over, if we look at this, just complete this right angle triangle, make it look a wee bit nicer. Yeah, whoa, dear me. To make this look a wee bit nicer, you've got your triangle in here. This is your angle theta. This hypotenuse was length 1. So if we want to find our x value, we're going to be using sine this time. So sine theta equals x over 1, which means then x is equal to sine theta. Now have a look at the position of the thing. It's over here, so it actually has to be minus sine theta. So I've just said here minus because it's left of the y-axis. Okay, to get your y, it's going to be y is the adjacent in this triangle. Y is adjacent, so you're going to be using cos theta equals adjacent over hypotenuse. So cos theta equals y over 1. So therefore we better rearranging y is equal to cos theta. So our x value goes to minus sine theta, and our y value goes to cos theta. So what we have found out, there we've said that again here, and it says therefore the matrix for rotation of theta about the origin is cos theta minus sine theta cos theta. So how we got that was just push those two column vectors together to get that, and that's it. We're now going to look at the reflection matrix. So again, we want to look first of all to see where 1, 0 goes to. So that's what we want to find. So I've done a drawing, and it's a reflection in a line through the origin. And this is a wee bit strange. This is a different way of doing it. We know that y is equal to mx plus c. Another way we could write that is tan theta. So if you think about why that is, there is a wee thing which has a gradient m. And what there's theta. Tan theta is equal to the opposite, which let's go really old school. That's your rise over your run. So tan theta is equal to rise over run, which we know is our gradient. So tan theta, quite simply, is equal to m. So here, in this one, we've got this point here. This is our 1, 0, and we want to reflect it in the line y equals tan theta, which means that the theta is the angle. So if it gets reflected, if that's theta in here, on the other side that's going to be theta, and this length is 1, so this length would be 1 over here. So we now need to find this triangle. We need to find that one was the whole thing there, so this wee bit here, we want to get rid of that, and this bit here we want to find is the x. So when I say x, I just mean from here to here, and we also need to find this height, y. Okay, what is the angle now? The angle is not theta, the angle is 2 theta. So if I do another wee triangle just to make it a wee bit clearer, because it's got very messy. There's my x, there's my y, we know this is 1, and that is now 2 theta. So we could just say then over here we've got it all done. Cos 2 theta is equal to x over 1, therefore x is equal to cos 2 theta, and sine 2 theta is equal to y over 1, so your y is equal to sine 2 theta. So hence 1, 0 goes to cos 2 theta sine 2 theta, and that's that one done. Okay, next up we're going to try and find where our point 0, 1 goes to. Now this is tricky, and it's really the angle part of it's tricky. Once we find all the angles, we're all right. It's not too bad, but it really is tricky at the start. Okay, in here, the angle is theta. We're reflecting our point 0, 1. And the line y equals tan theta x. So this angle here is theta degrees. If that's theta, then this angle would be 90 minus theta, because the whole angle here adds up to 90 degrees. And if it's being reflected in, oh dear me, it's being reflected in this line, then this angle down here is also going to be 90 minus theta. So that's where that comes from, that this is 90 minus theta. Okay, right, we're going to move away from this thing because it's a very confusing diagram, and we want to do this right angle triangle here, and that's what I've done up top. And if that was originally, this bit was 90 minus, that was the whole angle all the way down was 90 minus theta. This bit in here is going to be 90 minus theta minus another theta, because we are taking away this bit. So this angle is actually 90 minus 2 theta. So in here we've got 90 minus 2 theta. So I'm just going to redraw that triangle again, get rid of all the external markings on it. The length of the diagonal, the hypotenuse, is 1. This is now 90 minus 2 theta. And we want to find the x value, and we want to find the y value, so just using trig. So we'll find the y value first, and it says here sine of 90 minus 2 theta is equal to y over 1, or that's the same as cos of 2 theta is equal to y. So where that comes from, you know, for example, that sine of 30 degrees is the same as cos of 60 degrees, so sine of 30 really is equal to cos of 90 minus 30. That's all that is, and that's the same for vice versa. So likewise, cos of 30 would be equal to sine of 90 minus 30. So same idea here, so we can just change that to cos 2 theta. So y is equal to cos 2 theta. And also look at the position where the y is. The y value is beneath the x-axis, so you have to actually put it as minus cos 2 theta. Similar idea, you've got your cos 90 minus 2 theta is equal to x over 1. Therefore, sine of 2 theta is equal to x. So therefore, your x value is sine 2 theta. Your y value is minus cos 2 theta. So putting all those two column vectors together, you'll have the matrix for reflecting in y is equal to tan theta x is cos 2 theta sine 2 theta sine 2 theta minus cos 2 theta. Okay, a couple of notes about those. First thing to say is that they're both given to you in your formula booklet, thank goodness. And it says, and also then any rotation of the xy plane about the origin can be represented by a matrix of the form a minus b, b, a, where a squared plus b squared equals 1. And you can look back at what your formula was and you'll see it does work in that form. And any reflection in the xy plane in a straight line passing through origin can be represented by a matrix of the form a, b, b minus a, where a squared plus b squared equals 1. Okay, this next example says find a matrix representing a rotation of 90 degrees anti-clockwise about the point A, which is 3, 5. So to do this, I've filled in a wee bit of this to get us started. It says let the general point be x, y, and then what we need to do is we need to move the plane such that A, which is 3, 5, moves to the origin. We need to do this because our rotation matrix is only about rotating about the origin, not about any other point. So that means your general point moves to the general point was xy. It now has to move. It has to become x minus 3 and y minus 5 because you've got to get the point A, which is at 3, 5, back to 0, 0. And then we want to next thing we want to do is rotate through 90 degrees. So the rotation matrix, remember, was cos theta minus sine theta, cos theta. So just subbed in the 90 degrees here. Cos of 90 is just going to be 0. The sine of 90 is going to be 1, so that's now minus 1. Sine of 90 is 1, cos of 90 is 0. And that's what we have. Now all we want to do is multiply our new general point by that rotation matrix. So 0 minus 1, 1, 0 upon column vector x minus 3, y minus 5. And the last thing we want to do is translate this matrix such that A moves back to 3, 5, because remember that's what we did at the very start. We can't forget about that. So your last step then is going to be the 0 minus 1, 1, 0 upon column vector x minus 3, y minus 5, and then you've got to translate it back. So it's just a simple translation column vector, and that will give you your answer. Right, so just work through that and see what we get. So that was part of our explanation really. So how you would actually set this out then, your x dash, y dash, that's your new image point, is going to be, and then if you multiply, it's going to be 0 minus 1, 1, 0 times your x minus 3, y minus 5 plus 3, 5, and then we actually have to go through and do this. So your first step then, x dash, y dash, multiply out, that's 2 by 2 times a 2 by 1, that's going to be a column vector. We still have our plus 3, 5, and first row, first column, and so that's going to be minus y plus 5, and then second row, first column, that's going to be x minus 3. So then we get x dash, y dash is equal to, and that's going to be minus y plus 8, and then that's going to be x plus 2. Okay, now this is strange, but this happens every single time. You could rewrite this thing as 0 minus 1, 1, 0 upon xy. So notice all I've got here, that was my my rotation matrix that I used. That's the same thing. And then this bit is just going to be whatever these numbers are. So 8 and 2. So basically we have shown that this thing, that our rotation, we were doing here, rotation of 90 degrees anti-clockwise about the point 35 is equivalent to rotating anti-clockwise 90 degrees about the origin and then translating by 8, column vector 8, 2. But this always happens. If you do not believe me, folks, multiply this out and multiply that out and then add the 8, 2, and you'll see you do get this thing. It does work. But very easy for you to do this every single time. Once you get to here, provided you haven't made any mistakes, that you'll always just write down your second bit here is the column vector xy. The first bit is just a matrix, whatever you've done. And this applies to whatever it's going to be, reflection, rotation, enlargement. And so it's just the original rotation matrix that I had up here. And then this last column vector, which is just a translation vector, is just whatever these digits are. So that if that had been minus 4, it would have been minus 4 here. If that had been plus 16, it would have been plus 16 here. And that's it. Okay, last thing, just say the transformation is the same as rotating 90 degrees anti-clockwise about O, then translating by 8, 2. And that is that example done. Okay, this example says find a matrix equation representing an enlargement scale factor 3, center, -1, 4. Now we mentioned briefly earlier on in one of the earlier videos that the enlargement matrix is of this form. So 3, 0, 0, 3 would enlarge you scale factor 3, but it's scale factor 3, center of enlargement, the origin. So similar to the last example, we're going to have to move this back to the origin. So first thing we're just going to say let general point be xy, and say move such that -1, 4 goes to the origin. Sorry. Which means that's x plus 1 this time and y -4. And then what we want to do, so that's our first thing, that's our second thing, what we want to do then is enlarge scale factor equal 3. i.e. what we're doing is the 3, 0, 0, 3 times the x plus 1, the y -4. And our last thing then is translate back such that our point goes to, we'll just say our point goes to -1, 4. Right, so the last thing we want to do really is we've got our 3, 0, 0, 3 times our column vector x plus 1, y -4, and then you want to add on the -1, 4. Okay, so we'll just work through that and see how that goes for us. And we'll see the similar wee trick to the last thing, where you can rewrite it again slightly differently at the end. And you should be able to do this with ease. Don't overthink it, just believe in what you have done that it's correct. And we'll see how we get on. Okay, running through this as quickly as we can. Let's see, we'll go, this is now going to be a column vector. This is going to be 3x plus 3, and then that's going to be 3y -12, and another column vector -1, 4, and that is going to be the same as 3x plus 2, and that's going to be 3y -8. And this is the fancy bit. Remember, we want to just write this as some matrix times xy, and then plus some other column vector. So the column vector is easy bit to see. That's just going to be 2 -8, and the matrix is the enlargement matrix that we had at the start. So we'll just put that in and see what it looks like. So it's 3, 0, 0, 3, and that's it done. So in this one, you can see that is equivalent to really enlarging scale factor 3, center of enlargement, the origin, and then translating by 2 -8. Okay, this example says find a matrix equation representing a reflection in line y equals x plus 4. Now we don't know how to reflect in the line y equals x plus 4. So the first thing I'm going to sort out is getting into the form that we want. So we want that y equals tan theta x. So tan theta is a gradient. Here the gradient is 1, so tan theta equals 1, i.e. theta is equal to 45 degrees. Next thing is this thing has, it should have had an intercept of 0. This has an intercept of 4. So the y-intercept is at a, which is 0, 4. So we want to translate 0, 4 to the origin. So this is me taking my general point xy back to x and then y -4. We then want to reflect in the line y equals x plus y equals x, i.e. y is equal to tan 45x. So the matrix equation for reflecting a line y equals tan theta x was cos 2 theta, sine 2 theta, sine 2 theta minus cos 2 theta. So that's put in the 45, and you're going to get 0, 1, 0, 0, 1, 1, 0, and then we do that to our new general point, so 0, 1, 1, 0 to x and then y minus 4. Then you want to translate back to 0, 4, so just add in a translation vector, column vector of 0, 4. So your x1, y1 is equal to 0, 1, 0, 1, 0, 1, 1, 0, sorry, times x, y minus 4, and then plus 0, 4. Sort that out again, and you'll get down to this point. And then here, again, to do this, minus 4, 4 is the easy bit. Just put that in as a translation vector to be added on. And this thing should be the same as your original reflection matrix, and that's it. So you've got this thing is equivalent to a reflection in a line y equals x followed by a translation. Okay, folks, you're now ready to do exercise 6D, questions 1a, 2a, 3, and 4. Any questions, please get in touch.